In this video, we're going to talk about how to use the natural log to solve exponential equations. So remember we talked about continuous growth and decay equations in the exponential functions unit. We talked about exponential growth and decay using the formula n equals n naught e to the kt, and continuously compounded interest using the formula a equals p e to the rt. Remember the key to identifying when we need to use these formulas is we see the word continuous being used in the problem statement. So let's try this example. It says Janet opens a savings account with an initial deposit of $1,600. The account has an interest rate of 3% compounded continuously. After how many years will Janet have $3,500 in her account? The key word here is continuously. Okay, so that means we're going to be using the continuously compound interest formula, which is A equals PE to the RT. So we're told the initial deposit is 1600, the interest rate is 3%, and we want to know after how many years she'll have $3,500 in her account. So let's identify the key terms from the formula. So we have PE to the RT. A is going to be the value she ends up with, which in this case is $3,500. P is the starting value, which is 1600. R is going to be the rate, so that's 3%, which we go ahead and convert to a decimal. So that's going to be 0.03. And then T is what we're trying to find. So when you substitute in this formula, we have 3,500 equals 1600 e to the 0.03 t. So now we need to work on isolating that exponential term. So we're going to go ahead and divide both sides by 1600. So when we divide both sides by 1600, we have 3,500 over 1600 equals e to the 0.03 t. So now that the exponential term is isolated, we can go ahead and take the natural log of both sides. So we have 3,500 over 1600, and that is equal to the natural log of e to the 0.03 t. So now we have the natural log of 3,500 over 1600. And then here, the natural log and e to the 0.03, those are inverse operations. So that's just going to end up being 0.03t. And now we can divide both sides by 0.03 in order to isolate t. So now that we have t by itself, we can just go ahead and go to our calculator and compute its value. So I'm going to go over to Desmos here and type ln parentheses, and then I have 3,500 divided by 1600, and then I'm going to close the parentheses and then do divided by 0.03. So that tells me that the t value is going to be approximately 26.1 years because it tells me to round to the nearest tenth place. So now you can go ahead and pause the video and try doing this example on your own. So here we have a computer virus that begins with 40 infected computers and then spreads at a continuous growth rate of 10% per minute. How many minutes does it take the virus to infect 10,000 computers? So since it says continuous growth here, we're going to use the formula n equals n naught e to the kt. Let's identify the key values. The starting value is n naught, which is 40. We're going to end up with 10,000 infected computers, so that's n. K is 10%, which we convert to a decimal as 0.10, and we're trying to find t. So this is going to give us 10,000 equals 40 e to the 0.1 t. Isolate the exponential term by dividing by 40 and then take the natural log of both sides. So then we can divide both sides by 0.10. So we have the natural log of 10,000 over 40 divided by 0.1 is going to give us approximately the value of t. When we go to Desmos and type that in, we're going to get about 55.2 minutes as our value of t. So there's one more application of continuous decay, which is Newton's law of cooling. So this is something that happens when you have like a hot cup of coffee in a cold room. You know that if you leave it out for a while, the coffee is going to cool down until its temperature becomes the same as the temperature of the surroundings. So this equation right here is going to help us figure out how long that's going to take. And let's go ahead and look at an example using this equation. Newton's law of cooling states that for a cooling substance with an initial temperature of T naught, the temperature T of T after T minutes can be modeled by the equation T of T equals Ts times T naught minus Ts e to the negative KT, where Ts is the surrounding temperature. So surrounding temperature would mean like the temperature of the room. And K is going to be a constant that represents the substance's cooling rate. So we have a liquid substance heated to 70 degrees Celsius. Upon removing it from heat, it cools to 60 degrees in 10 minutes. If the surrounding air temperature is 50 degrees Celsius, what is the substance's cooling rate? So since it's asking us for the rate, it's telling us to find the value of K in this equation. Okay, so let's identify the variables in this equation. So T of T means the T after a certain amount of time, right? The temperature, and then what is the time frame we're looking at? It says 10 minutes. Okay, so T of 10 minutes, well, it tells us that it cools to 60 degrees. Okay, because that's going to be the temperature after 10 minutes. TS is the temperature of the surroundings, so the temperature of the room. It tells us that is 50 degrees Celsius. And then T0, T naught, which is the starting value, that's the initial value of the substance. Okay, so in this case, it says the substance starts off at 70 degrees. And then we have T, like lowercase t, representing the time, which it tells us is 10 minutes. So now we just take all of this information and plug this into this formula we have here. So we have T of T, so that's going to be 60 is equal to TS, which is 50, plus parentheses, and then we have T0, so 70 minus TS, which is 50, and that's e to the negative k times lowercase t, so that's going to be 10. Okay, all I did was substitute all these values from the problem into this equation. So now we need to simplify, and this is going to follow PEMDAS, okay? So I'm going to start off by simplifying what is inside the parentheses. So that 70 minus 50, that's just going to be 20. So we have 20e to the negative 10k, okay? So since this is an exponential equation, I need to go ahead and isolate the exponential term. So I start off by subtracting 50. So now we're doing the reverse order of operations because we're solving for the variable. So I start off by subtracting 50, and that gives me 10 equals 20e to the negative 10k. And now I need to isolate the exponential term by dividing both sides by 20. So 10 divided by 20 is going to be e to the negative 10k. Now that the exponential term is isolated, I go ahead and take the natural log of both sides. So I have natural log of 10 over 20 is equal to the natural log of e to the negative 10k. Well, the natural log and e will undo each other, so I have the natural log of 10 over 20 is equal to negative 10k. Now, in order to solve for k, all I need to do is divide both sides by negative 10, and that is going to allow me to approximate the value of k. So k, I'm going to go ahead and go to Desmos now, and I'm going to type in natural log of 10 divided by 20, and then I close the parentheses and do divided by negative 10. And this tells me it's about 0.0693. But look at this problem. It tells me to express as a percentage rounded to 2 decimal places. So I'm going to take this value that I have right here, 0.0693, and then I'm going to multiply that by 100 to convert it to a percentage. And that's going to tell me that K is approximately 6.93%. Okay, so that is going to be the cooling rate of this substance. So remember, exponential equations can be used to model many real-life situations. If there's an unknown value in the exponent, you can use logarithms to help you determine that missing value.